Okay, so today we're going to learn a new type of a modern iterative method. It's called the conjugate gradient method. This method is, excuse me, the details about the method is given in related to your textbook section 2.6.3. Okay, so before we're talking about this method, we'd like to talk about a type of matrix that is called the symmetric positive definite method. Okay, but before we do that, let's consider the transpose of a matrix. So if a matrix A is given by Aij, so I is a row number, J is the column number. So if we switch the Ij, we get another matrix which J becomes a row number, I becomes the column number. Then this is called the transpose of a matrix. Okay, so n by n matrix A is said to be symmetric if it equals its transpose, that is Aij equals Aji. So for example, if we look at the matrix A here, so we have 1, 4, 7, 4, 2, 5, 7, 5, 7. So if we look at the diagonals, right, so the matrix is symmetric along with its diagonals, right? So this guy equals that here, and the 7 equals that. Okay, so basically A transpose equals A. Okay, so to get the transpose of a matrix is very easy. You just rewrite all the rows into the columns of the transposed matrix. So for example, the first row is 1, 2, 3. Then it becomes the first column of this matrix. And the second row, 4, 5, 6, is the second column. And the third row is a third column. Okay, so generally for n by n matrix, we have that, how to compute the transpose. Okay, so rows of A becomes columns of A transpose. And here an application of a transpose, we can rewrite the inner product of the two vectors in terms of matrix multiplication. So let's say we have a vector, a column vector x1 to xm, and its transpose is a row vector like that. Okay, so the inner product of x and y is basically the transpose of x vector multiply y. So the transpose becomes a row vector, and the y is still a column vector, and we do the standard matrix multiplication. We end up with this inner product. Okay, so the definition of a symmetric positive definite matrix is that. So we use SPD for short. So first of all, matrix A has to be symmetric. That means A equals its transpose. And it's positive definite. That means for any x, this thing is greater than 0. Okay, so for example, we have this matrix that is SPD. So we can show that the A equals A transpose, so it's symmetric. And now we verify if this condition is satisfied. x1, x2 multiply matrix, x1, x2. And if we write this thing out, we end up with a number. Okay, so this is a number. We end up with writing out of the multiplication. And we reorganize everything. We can see the whole thing is square plus another square. So we know that this thing has to be greater than or equal to 0 because all the parts here is square. Okay. The property of symmetric positive definite method is that SPD matrix A is the SPD matrix if and only if all the eigenvalues of A are positive. Okay, so now checking the instead of checking this one for all the vectors x to make sure this guy is greater than 0, we only need to see if all the eigenvalues is greater than or equal to 0. If that's true, then this matrix plus this matrix is also symmetric. Then we say this matrix is SPD. Okay, so from the previous example, we can see that the eigenvalue here of this matrix are two eigenvalues. One is 6 and one is 1. And also A is symmetric. Therefore, A is SPD. Eigenvalues of a symmetric matrix are always real. We can prove that, but this is not the main point of this course, so I'm going to skip that. a very important numerical method that can be applied for solving SPD matrices is called the conjugate gradient algorithms. And so here is a detailed algorithm. I'm going to give it out here, and I'm going to explain what I'm doing for each step. Okay, so given the initial guess, we have that, and the initial residue is computed by b minus ax0. And we define another direction vector d0 that is given by the direction of the residue. And for the following iterations, we say that if my residue is still less than my tolerance, if my residue is less than my tolerance, then I can break. Okay, so I'm happy. This is my solution. Otherwise, I'm going to update 3 quantities. Okay, the first quantity is called alpha k, and that is a step length. This is given by the residue divided by this quantity. And once we have this the step length, then we're going to search my new approximation. That is by extending my previous solution in a direction in this direction with this step length computed here. And then after we computed this new approximation, we can update the new residue by computing my new residue that is given by here. This is my new residue. And then I can recompute some number beta k that is given by the alpha k plus 1 transpose, alpha k plus 1 here over the previous ones. And then this define my new searching direction that is given by this way. Okay, so why we're doing that is we are searching. So each searching direction we're given is perpendicular or orthogonal to all the previous residues. Okay, so we're starting with this residue here. And by doing that, we are ensuring that the new direction is orthogonal to all the previous directions. Okay, because we have a matrix of dimension n, and the number of residues we have is a number of linearly independent residues we're going to have is n. Okay, so by doing this, we're making sure all my new residue is perpendicular to the previous ones. Then at most we will have n perpendicular directions. Therefore, this thing should converge to the exact solution in n steps. Okay, so the more theoretical background for this method is a little bit harder, but here I'm trying to help you to understand. So this residue is to making sure that my new direction is always perpendicular to my previous residues. Once I got everything is perpendicular, then I'm done. Or you can stop earlier if you're happy with your residue. Okay? So here are some notes about applying this conjugate gradient method is that the most expensive part is to compute this A multiply D, a matrix vector multiplication. So that is used here and here. Because this one needs to be computed twice and it's expensive, we don't want to do the real computation twice. So the smartest way is to save this value once you compute it and reuse it here. Okay? So to avoid the compute a dk twice, we may save this vector. And also we notice that this RK, the inner product of the residue itself, the norm is used twice, right? So this one is used here, this one is used here, and the new one is computed here, and this new one will be reused for next step becomes old one. Therefore, we may want to save this to avoid the recompute RK to in our algorithm. Okay, so in the exact arithmetic, the conjugate gradient converges to the exact solution in at most n steps if A is an n by n matrix. And in floating point arithmetic, the conjugate gradient may not give the exact solution in n steps due to round-off errors. Okay, so here's an example that's showing you how we computed the conjugate gradient, how we computed the solution for this 2x2 matrix using CG method. Okay, so we started with my initial guess is 0, and my initial residue is computed by b minus ax0, and I'm using my initial residue as my direction here for searching for the new approximation. Then we compute my alpha 0, and then according to the this formula here, and I got my new solution, and I computed my new residue here, and I computed my new searching direction D1 here, making sure that is perpendicular to my previous searching direction. So this formula here is basically doing the projection onto that previous residue. Then my new direction is perpendicular to my old direction here. And after the second step, I will get an exact solution because this is 2x2, then we only need 2 steps to get an exact solution. So we do that, the same thing. Then we have the second residue, it has to be 0, right? Because this is dimension 2. Then we can, in a 2 dimension, we can have only 2 orthogonal residues. That's because on a 2 dimension, if you join the axis, you only have x-axis and the y-axis. They are perpendicular to each other or orthogonal to each other. So we got our exact solution for -1. This is a simple example.